Here's another video on optimization using derivatives, and we're looking at optimization with an angular quantity. So this is a fairly straightforward video. If you haven't seen that, one of the quantities that can change is an angle. Okay, so it doesn't have to be things to do with finance or linear quantities and things like that. It can be angular as well, and the way we handle it is not greatly different. So let's have a look at this example, and hopefully this will be sufficient for you to learn how to do these. And again, this is at a fairly basic level. All right, so it's an introduction, learning about angular quantities as rates have changed. Alright, so we've got an outdoor expo. It's a triangular area of land, and we've got to set up a display stall for that company there. And I'd hate to be the people next at the stall next to them because, yeah, well, you can read. So, as illustrated, the stall must border on to a fixed and solid partition. And if I just bring that up there, right at the bottom, you can see the partition. Okay, it's very long. Okay, and it's straight, and that's it. All right, it doesn't change. The organizers won't let you change it. All right, and that they must utilize these two boundary markers which lie along the ground. One's a straight line at 12 meters. The other one is a straight at 21, and they meet at a point there. Okay, it forms an angle which we'll call theta in this question. Alright, now with these constraints, determine the angle which provides the maximum area for the stall. So you can see we've got an area in there. Okay, and how can we maximize that area? So there's our differential calculus. As well as the angle, which maximizes the area, we want to find what this area actually is in square meters. We can work in radians or degrees in this one. So in questions like this, we need to go back to some of our early mathematics, and there is a formula for non-right angled triangles, because there's no way in the world we would just come out and assume that this is right angled. It might be, but what I mean by non-right angles, it can include right angled triangles, but it includes triangles with other angles as well, which we must be open to. So we're going to use this generic formula, which you should have seen at this stage. Half times side A length times side B length times sine of the opposite angle to side C. Alright, you might have seen that, and that, the symbols change, as you know. So in this one, I'm calling area A for our particular, I'm calling it symbol A for our particular application here. Subbing in the values for us, we've got, it doesn't matter which one we call A and B, alright, and we've got 12, half times 12 times 21, and we don't know what C is. C is an unknown at this stage. We can put that in. Alright, so that would be 100, simplifying 126 sine, I might call that theta, sorry, on that line there, to be a bit more consistent with how we set it up. Okay, so we have an expression for A in terms of theta. So really the function is A of theta. Okay, so theta changes A. Theta is the independent variable, A is the dependent variable, and they're both very relevant to what we're trying to find. Okay, so from our earlier work in optimization, we know we need to find dA d theta, the derivative of this function here, and that will help us find a stationary point. Alright, so we look for dA d theta, or we determine dA d theta. Alright, so that would be 126 cos theta. So the stationary point location is at the value of theta, where dA d theta equals 0. So what we do then, 0 equals 126 cos theta. So when we have 0 equals cos theta, we need to realize we have some restrictions here. Because it's a triangle, theta has to be between 0 and pi radians, or 180 degrees. And that fact clears things up quite nicely because trig equations often have more than one solution. So we only want the one solution, and so that clears things up very well for us. Now, regardless of whether you're working in degrees or radians, practically degrees would probably make more sense, but radians is an important part of our course, so either way, okay? But we know that cos of pi on 2 or cos of 90 is 0, and theta is pi on 2 radians, or 90 degrees. So the location of the stationary point is the place when theta is pi on 2. Okay, so now we know where it is, then we need to find the nature of the stationary point, and the best way to do that is pretty much the second derivative is the quickest way. So we need to find d squared, that should be an a, d squared a d theta squared. Okay, so the sign of that, SIGN, will tell us, or even if it's 0, let's hope it's not 0, the sign of that, whether it's positive or negative, will tell us the nature of the stationary point. We're hoping it's a maximum, so we're looking for a negative, hopefully a negative value for the second derivative here. And you'll recall that the second derivative is all about the concavity, so if it's concave down, that will also verify that that's a maximum. So before we found out the first derivative was 126 cos theta, so let's take the derivative of that to get the second derivative, and cos goes to negative sine, and so we have negative 126 sine theta. So the function for the second derivative is negative 126 sine theta, so at that point, which was pi on 2, at that point pi on 2, we sub that in. So we have d squared a d theta squared equals negative 126 sine pi on 2, or 90 degrees if you prefer in this case. And sine pi on 2 is 1, so we have negative 126 times 1. So that's a negative, so that means that the turning point, or the stationary point, is a maximum. Yay, because that's what we were hoping to find. Communicating the first answer out of the two then, theta equals pi on 2 radians, or 90 degrees if you prefer, gives a maximum area. Okay, so the maximum area occurs when theta is 90 degrees or pi on 2. So a right angled triangle provides a maximum area for us here. And the second part is, what was that area? So the area is half 12 times 21 sine 90 or pi on 2, and that's 126 times 1, okay, because sine pi on 2 or sine 90 is 1, which is 126 square meters. Is the maximum area.